Hi, welcome back to Missing Chemistry. This is going to be about molecular forces. Now, I want you to understand that when we talk about molecular forces, we're talking about two types of molecular forces. And we often call these things intermolecular forces. All right. Now, just stay with me on this, okay? Some people call them IMF. Intermolecular force, that makes sense. Basically, what goes on is it's an attraction that is between two or more molecules. So you have two molecules, or you can have more of them, or more molecules. All right? So this is kind of a basis thing. So we have two types of molecular forces. We have something called intramolecular force. And those are the forces. Those are the forces that hold compounds together. So forces that hold compounds together. And that's important to remember, okay? So that's within the compound. So we're going to say within the compound, okay? So now, one of those forces is what we call covalent forces. Now, a covalent force, or a covalent bond, as we would call it, covalent bonds, of course, are between nonmetals and nonmetals. And that's important to remember. Okay? Very, very important to remember. Now, so covalent bonds can either be what we call covalent, where we share electrons equally. So in other words, the electrons that are shared between the two nonmetals are shared the same amount of time. And there's something called a polar covalent bond. And that's also important to remember, that we share electrons, but not equally. So in other words, the atom that is more electronegative is going to have the electron being pulled towards it. Now, the next type of intramolecular forces is something called an ionic bond. All right? Ionic bonds they differ from covalent bonds because they're between metals and nonmetals. All right? We don't share electrons at all, so there's no sharing of electrons at all. It's kind of like a give electrons or take electrons kind of situation. Okay, and that's important to remember. And last but not least, there's this really weird one where it's something called a metallic bond. Now, a metallic bond is kind of strange. It's between metals, basically. Sorry about that. It's metals and metals. And what happens is you have, the best way I can describe it are metal cations. And a cation is a metal that has given up its valence electron, right? So it's metal cations in a sea of electrons. So it will look something like this. Here's a cation right here. Here's a cation right there. And there's a cation here. And you might have a cation here. You could have a cation there. You have a cation there. Right? And you have all these electrons, kind of like, in between these guys, all around these guys, just swarming the thing totally up. And so that's the three types of intramolecular forces. Now there's something called intermolecular forces, which is a little bit different. So let's go ahead and erase these guys here. And we'll go and get rid of this guy right here. Let's see. It's probably take two erases. The circle doesn't last forever. All right, so let's kind of look at this a little bit differently here, okay? All right, now, while we're talking about, and we're going to call this intermolecular forces, so I can just use that again. Let's see here. Now, intermolecular forces are between molecules. So it should be two or more molecules, and it should be written as between the molecules. All right, and so we're going to call this intermolecular. Now, the first intermolecular force, I guess we could talk about, is the strongest one. The first one's called hydrogen bonding. All right. And so basically with hydrogen bonding, we have a situation where we're going to have hydrogen bonding with three other elements. Hydrogen's going to can bond with fluorine, oxygen, and nitrogen. So when hydrogen bonds with any of these characters here, you're going to create something called a hydrogen bond. And the most famous one we can think about is water. Think about this. So water basically looks something like this. So you've got, a structure that looks like this. And by the way, water is a polar covalent molecule. Okay? And so now what we have going on is this. We have a dipole. Now a dipole, we'll show you what a dipole looks like. Basically, they're sharing electrons, right? But in this case, hydrogen is becoming positive, where oxygen is becoming more negative. Again, here's the dipole here, showing that hydrogen is going to become more positive, and again, oxygen is going to become more negative. Okay, now, I'll put that, just to kind of symbolize that over there too. Okay, so what happens is this. When hydrogen becomes more positive, you'll have another water molecule that's kind of like over here somewhere, right? And you're going to set this up like this. And, hey, watch this. This hydrogen is becoming positive. This hydrogen is becoming positive, but this oxygen is becoming negative. See that? So this negative right here and this negative and this positive right there are going to kind of make a temporary bond. And that's looking really kind of messed up looking. So I'm going to try to clear some of this up here. And it looks like I'm going to need the eraser here. And I'm going to go there. And so you're going to get a temporary bond, or a very strong bond actually, between that hydrogen and that oxygen. And that thing right there is called your hydrogen bond. Now, you can also do this with, say, fluorine. All right, so let's see. Let's try one with fluorine. Okay, what would that look like? Okay, all right, got it. So you have H here bonded with our fluorine. And we'll try this here. And then you might have another hydrogen fluoride over here, just kind of like floating around, right? And so look at this. There's the dipole. Fluorine is going to definitely attract that atom, not atom, but that electron, and it becomes negative there, sigma negative, where hydrogen becomes sigma positive. Now remember, hydrogen's not giving it up. It's just kind of like, sharing it, but not sharing it equally. So in this case, we have a dipole that goes this direction, and that's there. And of course, this becomes sigma negative, and this becomes sigma positive. So you make a dipole bond that now exist between this hydrogen and fluorine. Okay, and that's the dipole bond there. Now, there are other, and I'm going to put a dipole here. This is our dipole-dipole bond. And this is our second bond type. Dipole, and I'm going to write dipole again. Because you have two dipoles. You got a dipole here, you have a dipole there. And that would be our second one. So it would be dipole-dipole, or dipole. Dipole-dipole. So, okay. Now, and it deals with basically, definitely polar molecules. And you would see this in polar covalent bonds. I would call them PC, polar covalent. Okay, last but not least, you got this really weird bond. So let me go ahead and erase this again. Give you guys a moment to look at that. You guys got it? Great. So let's go ahead and get rid of all this stuff here. I know it's been a little bit cluttered, but it's going to be okay here. So get that there. Oh, yes. And while you're watching the circle, you could be looking at this dipole-dipole thing here. Oh, not anymore because it's gone. All right. So last but not least, we're going to look at the final bond, which is called London Dispersion Forces. Sometimes we call these things van der Waals forces or van der Waals forces. And if you see either name, guess what? They mean the same thing. And these guys are like temporary dipoles. Which means they're there one moment and they're gone the next. A classic example of one of these guys, let's say, let's try oxygen. Okay, so oxygen looks something like this. So you've got, of course, one character there. Okay, you're going to have a double bond, and then you're going to have there, and there, there, and there. All right. So you're going to have a situation where one of these guys is going to want to go kind of move over one of these electrons or electron pairs. This pair right here might decide to float over this direction here. And when it does, it's going to create a temporary dipole. So this oxygen here is going to become more positive, and this oxygen is going to become more negative. And again, you might have another oxygen over here where this oxygen is double bonded up to this oxygen here. And then, of course, if this pair slides that direction, then you have a dipole that's going to look like this. And this oxygen is going to become, of course, definitely more positive. And this oxygen is going to become more negative. So then you're going to get what we call a very temporary dipole. And it's going to form, it's going to be there for a few moments, and then it's going to be gone. You know, this one's kind of hard to see. The classic one that most people do when they talk about these dipole-dipole van der Waals forces, they like to talk about nitrogen. I mean, you know, they say nitrogen. Okay, so nitrogen basically looks like you have two nitrogen because it's also a diatomic element. And you have a situation where you have this situation here. And then you have another nitrogen here set up like this. And this is the classic one where, okay, hey, you know, let's say this dipole, these unshared pair electrons are temporarily attracted towards this direction, right? So these guys are actually going this direction. And when they do that, this nitrogen is becoming positive, and this nitrogen is becoming negative. Well, the next molecule by it might also be doing the same thing. And this, of course, will do something similar where you have the dipole right in this direction. And then this nitrogen becomes, kind of positive. That was an ugly looking sigma symbol. And this will become negative. So therefore, then again, you have your temporary dipole. And again, it's very temporary. So guys, here are intermolecular forces. Hydrogen bonding is the strongest. The second strongest one is the dipole, and basically dipole, and it deals with polar molecules, which we call polar covalent. London dispersion forces, and van der Waals forces are the weakest, and there are temporary ones. So you guys be snarly. We'll see you back here at Musin Chemistry.